This is a video going over Section 3.4, which is the start of rational asymptotes, rational functions, and today we're gonna be talking about asymptotes. So we're gonna start by graphing the reciprocal function, which is the function 1 over x, and you can plot some points to get the idea of what this looks like. For example, 1 goes to 1, 2 goes to a half, 5 would go to 1/5, 10 would go to 1/10. So it's getting smaller and smaller as x gets huge. But if I put in a half, then the output's going to be 2. If I put in a tenth, the output is 10. So the graph, when you put in positive x values, is looking like this. And on the negative side, similar situation. Every time I put in a negative x value, there's going to be a negative y output. So the graph, the reciprocal function looks something like this. Is this continuous? Nope, it is discontinuous at x equals 0. Domain and range, the domain is everything but 0, and that is true of the range as well. And all right, so let's talk about something that's a calculus concept, and we're talking about, and we're going to write it as such. What's happening to the function as x is getting huge, both positively and negatively. In other words, as x is going to infinity and negative infinity. So as x gets huge, what is happening to the y values? Well, the way we write that in calculus is we're going to call it the limit. So the limit as x approaches infinity of the function. So this function f of x, our reciprocal function, as x gets huge, the y values are approaching 0. And as x goes towards negative infinity, the y values are also approaching 0. And we call that a limit. What are the y values approaching as x is getting huge, both positively and negatively? Well, let's look at what's happening as x is going towards 0. And we're going to break this down into two parts, because one thing we can say is the limit as x goes to 0. And when I put that little minus sign above the 0, that means if I'm coming from the left of 0. So as I'm going towards 0 from the left, the y values you can see are going towards negative infinity. But if I'm going towards 0 from the right, and I'm going to indicate that by a little plus sign, the y values actually are going towards positive infinity. So that's using that limit notation. It's just meaning what are the y values approaching as x is approaching a certain value. That's something we'll use in calculus, so I'll continue to reinforce it here. So as you may have noticed in the graph, as x is getting huge, it's getting closer and closer to 0. And as x goes towards 0, it's getting either closer to positive or negative infinity. Well, something that a graph gets closer and closer to is called an asymptote. So let's talk about some types of asymptotes we can have with rational functions. The first type is a vertical asymptote. So we say that if as x approaches a certain value, so I'll call it a, the y values go towards positive or negative infinity. In other words, the graph is exploding positively or negatively. Then we say x equal a is a vertical asymptote. And I'm going to call vertical asymptote VA. So if you're looking at a graph, you're going to have a vertical asymptote where the graph is exploding towards positive or negative infinity. So in this case, the vertical asymptote, we're going to say, is at x equals 0. And then let's talk about another type of asymptote, an end behavior asymptote, which I'm going to refer to as EBA. Well, so let's go here. So if as x goes towards positive or negative infinity, the y values either go towards a constant, like a number, b, or the y values go towards a function, then y equals b or y equals g of x is an end behavior asymptote. So end behavior, we've heard that before. when we've talked about polynomials, it's what is happening to the graph at the extremes, towards positive and negative infinity. And with rational functions, sometimes we're going to find them going towards a particular number, like the y values are going towards 2, in which case we'd actually have an EBA that's a horizontal asymptote. But sometimes we're going to have an EBA that is another graph that isn't a horizontal line, say a slanted line or say a parabola. So you're going to find all different types of end behavior asymptotes. But for the graph we just drew here, the end behavior asymptote as x is approaching both positive and negative infinity, the EBA is y equals 0. And you always report these as x equals or y equals. Don't just say a number. Tell me what it is, because it's some sort of graph, the EBA or the vertical asymptote. And when we draw in an EBA or a vertical asymptote, any time we draw any sort of asymptote, we draw them into the graph as dotted lines. It's a little bit harder when it's on the axes, but there you'll usually see in my solutions me drawing dotted lines to indicate the asymptotes. Okay. So let's do a different type of graph. So take a minute to see if you could draw y equals 1 over x squared, and then come back to this video. Okay, so y equals 1 over x squared. Very similar to y equals 1 over x, but one thing I notice, and it's good to get good at noticing these types of things, is this function's an even function. Every time I put in negative x, I'm going to get the same as if I put in positive. And all outputs are going to be positive, so it's going to look like this, more or less. And it appears that there should be a vertical asymptote and a horizontal asymptote, which is the end behavior asymptote. So the domain here is everything but 0, just like the reciprocal function. The range, though, is 0 to infinity, only positives. There's a vertical asymptote, it appears, at x equals 0, and there's a horizontal, which is a type of end behavior asymptote, at y equals 0. All right, so given this 1 over x squared, let's transform the graph to draw something like we have below. It's good to practice our transformations. Let's just make sure we have the order of this down. The first, with the x values, you would go left 2, which means for my vertical asymptote, which normally, as we just saw in the graph we did, is at x equals 0. Now, because I'm going left 2, it'll be at x equals negative 2. And then for the y values, I'm going to be flipping it over the x-axis. That's what that negative 1 is. So flip over x-axis and then shift down 3. So that shift down 3 is affecting my EBA. So instead of y equals 0, it's going to be at y equals negative 3. And then my graph is going to be now down here. So again, just a rough sketch of what's happening. The domain, it says find the domain and range. So now the domain is everything but negative 2. And the range is negative infinity to negative 3. All right, so that's just a little bit of what a vertical asymptote and an end behavior asymptote are. Now let's talk about how to actually find them. And there's a few scenarios, particularly, vertical asymptotes are more straightforward, but there's a few scenarios for end behavior asymptotes. Okay, so a vertical asymptote, remember that those are, you can spot it if you have a graph, it's where the graph explodes, like going towards positive or negative infinity. So if we remember our range analysis, that occurred when you were dividing by super tiny numbers. You'd get that explosion in the y values going towards positive or negative infinity. So how you find where vertical asymptotes are is where the function is undefined. In other words, where the denominator equals 0. So to find a vertical asymptote, it's always pretty straightforward. If there is one, you set the denominator equal to 0 and solve. So in this case, I would do 2x squared minus 5x minus 3 equals 0. Again, to find my vertical asymptotes. And I'm going to factor this. So it factors to, let's see, minus plus. So it's going to be a vertical. Oh, and by the way, this should be, and you're going to see why this should be the case. There's an error in my numerator. I should have 2x minus 1, not 2x plus 1. Because if I had 2x plus 1, something else is going to happen. So that should be 2x minus 1. Anyway, so vertical asymptote x equals -1/2 and x equals 3. And so those are your vertical asymptotes. That's where the denominator equals 0. And remember, as we said before, as you get closer and closer to 0, you're going to get that explosive in the denominator. That would have your function go towards positive or negative infinity. Now, there could be a case where you do not have vertical asymptotes, and that would be if you had something in the denominator that would produce only imaginary values, like x squared plus 1. Then you would have no vertical asymptotes. Okay, so now let's shift to end behavior asymptotes. What's happening as x is approaching positive and negative infinity? And again, we're going to do a little bit of kind of calculus notation here. And to get at the idea of the rules, the first thing you're going to do is you're trying to figure, what I'm trying to figure out here is the limit as x approaches both positive and negative infinity of this function. Is it equaling a particular value or another function? And the strategy to get at what we're going to define as the rule is to multiply the numerator and denominator by one of the variable of highest degree. So in this case, I notice the highest degree is x to the 5th. So I'm going to multiply the numerator and denominator by 1 over the x to the 5th. Because right now, if I plug in infinity, I'm getting infinity over infinity, which is undefined, mathematically undefined. So in multiplying the numerator and denominator by 1 over x to the 5th and distributing, I get 4 over x squared minus 3 over x cubed minus 1 over x to the 5th divided by 9 minus 2 over x to the 4th plus 7 over x to the 5th. And now if I think of plugging in huge values for x, all of these with a number over a variable are going to go towards 0. So all of these are going towards 0. And I'm left with 0 over 9, which is equal to 0. So in other words, this gets at this rule that if the degree of the numerator is less than the degree of the denominator, or in other words, I sometimes say the function's bottom heavy, it's greater the degree in the denominator, the EBA is a horizontal asymptote at y equals 0. So that's rule 1. Bigger degree in the denominator, EBA is y equals 0, which is a horizontal asymptote. And you can always test it out by multiplying the numerator and denominator by one of the variable of highest degree. Okay, so this case, again, EBA here was y equals 0. All right, well, what about if the degrees are the same? So let's go about doing the same strategy, multiplying the numerator and denominator by 1 over the variable of highest degree. So in this case, it's 1 over x to the 4th. And we're going to get 6 minus 3 over x squared plus 8 over x to the 4th in the numerator over 11 minus 5 over x to the 4th. Whoops, x to the 4th. So all of these pieces here with a constant over a variable, as x gets huge, all those will tend towards 0. And I'm going to be left with, when I plug in huge values for x, I'm going to get this limit as x goes to both positive and negative infinity of this function is going to end up being 6 over 11. So that means, once again, I have a horizontal asymptote for an EBA, but it's going to be y equals 6/11. And so what does that mean for our rule? Well, it means if the degrees are the same, then the EBA is y equals the leading coefficient of the numerator, which in this case was 6, over leading coefficient of the denominator, which was 11. So, which once again, it will be because it's y equals a constant, this too will be a horizontal line, and it will be the leading coefficients over each other. We'll tell you what that constant is. Okay, so those are the best case scenarios when you get one of those two situations. It's this third situation that is the most interesting / tricky, when the degree of the numerator is greater. Okay, so let's tackle. So, if the degree of the numerator is greater, if I think about putting in huge values of x, again, we got this infinity over infinity, and intuition tells me, well, since the degree in the numerator is greater, I feel like it is going towards infinity, which it is, or negative infinity, but like maybe it's going towards it in a particular way, not just, so we got to figure out, is it going towards it, but along a particular function? So right now, the way it is written, like with this particular example, I have no idea what the EBA is. So in order to figure it out, we're going to rewrite this function. And to do that, we're going to do division. Because remember when we did division, we had a dividend, we had dividend over, or we used a polynomial often in the last section, in the last like few sections. Dividend over divisor, we said, equals quotient plus remainder over divisor. So let's do that here. We've got our dividend, which is the numerator, over our divisor, x plus 3, and let's find the quotient and the remainder. Thankfully, this first example I've given you, because the divisor is of the form x minus c, I can use synthetic division, so I'm going to do that. So I'm going to put my c values -3. Make sure you put the coefficients of the numerator, or the dividend, up top, and there was no missing degree, so I didn't have to put a placeholder. And then let's do this. So -3, -5, -15, a positive 15, sorry, 16, and then -48, and there's a remainder of -53. And we want a remainder at this point. If we didn't have a remainder, it would mean that x plus 3 divides into something in the numerator, which is going to have a whole different set of issues that we'll deal with later on. So, but we're going to use the fact that this over here to rewrite our functions. So in other words, we just found that our function, another way to write the dividend over the divisor is this quotient, which is, since I divided the third degree by a first degree, I'm going to have x squared minus 5x plus 16 plus my remainder, which is -53, over my divisor, which is x plus 3. Now, if I think of plugging in huge values of x, so the limit as x goes to positive or negative infinity, this piece is going to go towards 0. Remember how we talked about in the previous, when you have a variable in the denominator and a constant in the numerator, that's going to tend towards 0. And so what you're left with is, in fact, the EBA. So the EBA in this case happens to be a parabola. So my EBA is y equals x squared minus 5x plus 16. And it's always going to be the case that when the degree of the numerator is greater than the degree of the denominator, the EBA is going to be y equals the quotient when you do that division. You're going to see how the remainder comes into play a little bit later on. So that's why I find it is important still to rewrite this. I know people like to find the quotient and then be like, oop, done. But rewrite it in this form, because you're going to find that rewriting this form is going to be helpful when we jump into graphing. All right, let's do one more example. This is a typical case when you get, instead of the EBA being a parabola, which it was in that first one, this EBA is a slanted asymptote, which is often called an oblique asymptote, which is just a non-horizontal or vertical line. So I can do synthetic again. I need a placeholder for the linear term. So bring down the 1, again, just doing your synthetic division. And so this means my function now can be written as x plus 1 plus 5 over x minus 1, the remainder over the divisor. As x gets huge, this goes away. So once again, the quotient is my EBA. So my EBA is y equals x plus 1. So it's a line it's a horizontal, or we call it oblique slanted asymptote. Okay, so now try some examples and the practice homework problems.